We're back. It's a great day for Gauss-Bonnet. In this video, we're going to use the Gauss-Bonnet theorem to come up with a definition for discrete curvature at a vertex on a triangulated surface. We'll then use this definition to show how we can reduce the size of some of the objects we're working with by removing vertices that have small curvature. To do that, we'll need to talk about a data structure to store our triangulation. So we'll also do that. Let's dig in. Okay, it's a great day for Gauss-Bonnet. We're up to video 5. So last time, what did we do? We talked about the Euler characteristic. So that's a global property. For us, we're usually going to have a triangulation. So we can compute this by taking the vertices, the number of vertices minus the number of edges plus the number of faces. And doesn't depend on the triangulation, which is crazy, and it doesn't depend on how we bend or stretch our surface, which is also interesting. So then we had all our pieces of the Gauss-Bonnet theorem. What did we say? If we're adding up our Gaussian curvature on the interior of our surface plus the geodesic curvature on the boundary, we get 2 pi times the Euler characteristic. Super cool theorem. So this is a local result on the left equal to global result on the right. So that was last time, and we revisited some examples last time. Feedback, I'm going to try to make the videos shorter, but once I get going, there's just so much I want to talk to, so it's difficult, but that is a goal, to make shorter videos. I'm trying. So in this video, what are we going to do? We're going to come up with a formula for discrete curvature. So if we have a vertex, let's say this is our vertex V, and we would like to say how much is our triangulation curving there, we can use the Gauss-Bonnet theorem to get this formula. So spoiler alert, this is going to be our formula where these alpha i's are the angles of the faces incident to V. So discrete curvature is kind of a oxymoron maybe, but we'll see the Gauss-Bonnet theorem really helps us. And then we'll look at an application of this as data simplification. If we have a triangulation with 0 curvature or even very small curvature, we might be able to simplify our objects by removing, some faces and vertices without really changing our geometry. So we have this square is represented in 2 ways, but on the right here it has much lower complexity. So in order to do that, we'll talk about a data structure for storing triangulations as well. That's the half-edge data structure. Okay, so let's consider a triangulated surface. Here's a picture from Wikipedia of a genus 3 surface, lots of triangles. They're difficult to draw, so I stole a picture. So how should we define the curvature at a point on a surface, and maybe even be more specific if this is triangulated? Because if it's a smooth surface, we have Gaussian curvature will work just fine for us. And the answer is use Gauss-Bonnet. And we'll see that we have some guides for what we would want. So if we had a total flat, so we would want our curvature to be 0. If we had this sort of positive, if it can be approximated by a smooth surface with positive curvature, we want positive curvature, and similar with negative curvature. So we'll see that the thing we define agrees with our intuition, which is, of course, always great. So this is like a major application of the Gauss-Bonnet theorem. When I first started this project, I was going to title it using the Gauss-Bonnet theorem because of using the Borsuk-Ulam theorem. So I started collecting applications, and this was one of the first ones, so I'm excited to share. Okay, so on smooth surfaces, geodesic curvature was maybe a little less intuitive than Gaussian curvature, but on discrete surfaces, geodesic curvature is maybe more natural. So if I'm interested in the geodesic curvature, let's say at this point, what is geodesic curvature measuring? It's how far you are away from being a straight line. So I could extend this, and my geodesic curvature is somehow going to be this angle here. So this is our geodesic curvature on the boundary. Oh yeah, I'm getting a little bit ahead of myself. So if we're defining curvature at this point, our first move is we're going to be performing some surgery, and we're going to consider cutting out the triangles incident to the vertex V, where we want to compute this curvature at a point. And so back to what I was saying about geodesic curvature, we can calculate that in terms of these two angles. I'll call this beta I and this gamma I plus 1, since it's on the next face over. And so our curvature is going to be, well, at a point is going to be, pi minus this quantity, beta I plus gamma I plus 1. And if we want our total curvature around the entire boundary, we can sum all of those up. So we'll add them up, and we can rearrange some terms here. So this will be sum pi minus beta I plus gamma I, because this gamma I is going to appear in one of our triangles. So we can just count it in a different rearrangement of our sum here. And we notice that this sum is, each term is equal to this alpha I here. So we get a nice formula for our geodesic curvature is the sum of these alpha i's. We can then use our Gauss-Bonnet theorem to come up with a formula for the Gaussian curvature at our vertex here. So what do we know? Well, we know that we're searching for Gaussian curvature. We know geodesic curvature. This is going to be sum of our alpha i's. And we know our Euler characteristic. We did surgery, so we have a disk. So this is 2 pi times 1. And then we get to this great formula. So our curvature at our vertex is going to be 2 pi minus sum of these alpha i's. And this is like super cool, very useful thing. So let's emphasize that a little bit. And we can check with our intuition if our surface is totally flat, then this sum is going to add up to 2 pi and we get 0 curvature. And that's exactly what we want. And we can do the same thing with positive and negative curvature. So this is a nice formula for discrete curvature. So the Gauss-Bonnet theorem gives us a way to define discrete curvature. There's other ways, and they'll agree with this, but this is maybe the most direct, so I really like this application. Okay, so let's put this to work in simplifying some of our surfaces so that our algorithms run faster. Well, if we want to talk about algorithms, we have to come up with a storage system for all of our triangles or whatever our objects are made out of. Most of the time we'll assume triangles. And so we're going to use a half-edge data structure, or sometimes called a D-cell, doubly connected edged list, I believe. And we have to exploit some nice facts. So since we're in a surface, we know that we have this nice order around a vertex. So we don't have, edges just pointing out everywhere. We can cyclically traverse around a vertex. And each edge is incident to 2 faces at most, unless we have a boundary. And so we're going to use those 2 facts to help guide us in this data structure. And what we're going to do is we're going to store things mainly in terms of the edges. So for each edge in our triangulation, we're going to record 2 edges, one going one way and one going the other way. And we'll have some nice functions. So for each edge, we'll map to its twin. So Tij would map to Ji, so notice order matters here, and vice versa. If we do it twice, we get back to where we started. What's that property called? Idempotent, I believe. And we'll also have a next function. So if we go Nij, we'll get out Jk. So with these 2 functions, we can really move around our surface and compute pretty much everything we would want. So if we want to traverse the boundary of a face, well, we can start with an edge on that face and just keep hitting next, next, next until we get back to where we started, and that'll traverse the boundary of a face if we want to do that, or if we want to traverse the edges incident to a vertex, we can go, you know, this one, then back and next, and there's a way to do that. I'm not being very specific here. So what do we have total? Well, for each vertex, we're gonna contain an edge that it maps to. So again, if we want to traverse the edges incident to a vertex, this will enable us to do that. So if this is, let's say V1, V2, if I have EV1 would give me the edge V1, V2. For the edges, I talked about we have this twin, so half edge means we're storing two edges for each edge so that appears geometrically. So we'll have twin. Next, we'll also map to the vertex. I believe usually it's the starting vertex, and the face to the left, I believe, is usually how it works. So we'll have those maps. And for each face, we'll record a single edge that's on the boundary of it. And it really doesn't matter because, again, we could iterate around the face. So that's our data structure that if someone says, here's a triangulation, and we talk about algorithms, I'm assuming that I have these operations. Okay, so here's our application. So we have this formula for discrete curvature from the Gauss-Bonnet theorem. Very nice, we can compute it. And if someone gives me some big triangulation, so I drew a picture here, but imagine even bigger, with lots of vertices. So this thing has, you know, you could count them, a lot of vertices. And one thing I might want to do is just change the color. So I'm rendering this and I want to produce a new color. So it's green now and I want to turn it to blue. Well, what could I do? Well, one thing I could do is iterate over all the faces, and for each face reassign the color to be blue. So that's a simple algorithm, but what does it require me to do? It requires me to iterate over all my faces. So before we even begin doing this or running this algorithm, one thing we could do is compute the curvature at each point. And if the curvature is 0, I could remove that vertex and combine some faces and remove some edges and significantly reduce the storage size of my object that maybe I have to recolor it 1,000,000 times. So I'm really, you know, this for loop is running 1,000,000 times. Well, if I can say reduce the size of my input by half, I've made a dramatic improvement here. So that's the power. And I tried to draw a picture here. This has fewer vertices, but I maintain triangles. Maybe you could even lose triangles in some cases, in which case you could have fewer faces. So this is a powerful application of the Gauss-Bonnet theorem. We're not speeding up our algorithm in this video. Next video, I believe we will study that, but we're compressing our data without losing any information. If we're just saying that, you know, removing if kv equals 0, you know, remove v, well, our geometry of our surface is staying the same because what we're removing is completely flat. So that's no loss of information to gain this this data compression that leads to a faster algorithm. So that's pretty cool. Oh, here's another great picture. This is Max Planck, I believe, from the paper Interactive Geometry Remeshing by Lesmeyer and Deshburn from 2002. So they're saying every time something is built from a scan, so some triangulation, so we built Max Planck from some scan here, it requires a complete remeshing. So we went from here to here. So this curvature calculation is being done over and over and over again. And then maybe we could consider, well, let's remove some of the points that aren't really adding too much. So we have lots of points here on the forehead area that have very small curvature. So now instead of removing 0 curvature, I'm just removing some threshold. And we can see we still get a pretty good representation of Max Planck here. And around the ear, we have lots of curvature, so we're going to retain a lot of vertices there. But on the forehead, things are a little bit smoother and we can get away with less. And maybe in your application, you're willing to tolerate some sharp corners. Well, you can use even fewer triangles. So that's a cool picture. I love this picture. It shows that this still looks pretty good, but it has way less triangles than this. So if you have to repeatedly iterate over all the triangles in your mesh, you're saving a lot of time here. Okay, so what do we do in this video? I'm going to wrap it up. We came up with a formula for discrete curvature using the Gauss-Bonnet theorem in terms of the angles incident to a vertex. We'll see this again. I believe we'll talk about a discrete version of the Gauss-Bonnet theorem soon. We talked about a half-edge data structure to store our meshes, so that'll be useful to us. And we saw how this could be used as a data compression application where we remove some triangles from our objects that aren't really having a big impact on what our object looks like. So cool application. Next time, I'm not sure what we're doing. I'll come up with something. See you next time. Thanks for tuning in.